𝐀𝐩𝐸𝐿 collaborated with 𝐀𝐩 Sri Lanka. As you already know, this webinar series is conducted mainly targeting the dynamic individuals who are planning to contest at the competition NASA Space Up Challenge 2021, the International Hackathon Program. At the very beginning, please excuse said Sabre for rescheduling the second session to this time slot due to unavoidable circumstances. So stay connected with us. Today's interesting session is on the topic applications of GNSS systems. No doubt the session will be very interesting and priceless, informative, as there is such an expert figure with us to share his valuable experiences. Before handovering the session, I want to request you that if you have any doubts or feedbacks, please clarify them at the Q&A session conducting after this session. So no need of any spaces more. I hand over the session to that nice personality, today's guest speaker, Mr. Chrishan Fonseka, geodesist at Lantmäteriet, Sweden. Over to you, sir.
Thank you, Kushlani. So good evening to all of you. I was invited by Said Sabra to conduct a lecture regarding applications of GNSS. So the main target of this lecture is to focus especially the undergrads who are interested in geospatial sciences in the GNSS field for them to explore the data sources, the possibilities, the topics, or what aspects to be touched in regarding this matter. So I've removed all the equations, no mathematics, it's just a story. I will be just explaining each and every topic so that you know, okay, there is a topic like this, there is an area of a study like this, there is an aspect like this. So if you are interested, you can further continue, you can create apps, you can create Python codes or programs to work further on this. So directly going before to the applications, let's just have a recap of the GNSS. So this is an overview. When you talk about GNSS, there is a space segment that, of course, we know the satellites, there are various constellations belonging to various countries. Then there is the control segment, which we don't pay much attention to, but they are the masters. They are the ones who uploads the messages, the correction parameters, gives the navigation instructions or other various parameters, which is especially the telemetry and command and everything. Instructions for the satellite to move and the instructions for which messages to be sent to the user. And then the user segment, that's us who is holding the receiver in our hand. So three main segments: the spaceborne satellite, which has a certain electronic system with an atomic clock inside that thing. The control segment, the master control station, and there are other several control stations as well, which monitor the locations and other health information of the satellite constellation. Then the user segment. This is basically the theory behind giving you the location. It's trilateration. For example, if you are in Colombo and somebody asks you where you are, I am near to Colombo, will not give you the exact location. You can draw a radius, or you can draw a circle, and you can be anywhere inside that circle. So it's at least, I mean, this is in 3D in real world, but you could see that at least you need 3 satellites. And this is like the position estimation error, the small circle in between. Actually, that's kind of related to the DOP values as well. The probability of user existing lies within this small circle. The thing with GNSS is you need 4 satellites because there is a time bias as well. So 4 unknowns, 4 equations, then you can solve for the position estimation based on the range of the satellites. So each satellite will be giving you distance. Based on that, you can calculate where the position is. GNSS, GPS, like for example, in my days it was very confusing for me what the hell is GNSS and what's GPS, but now of course you guys are much updated and you are like born with the technology in your hand. So you probably know, okay, GPS is this, and like if I give you a brief introduction, GPS is belonging to US. These are like the godfathers, the people who started this by the DoD of USA. And then they started giving them to the civilians as well. And then other countries started their own satellite systems, navigation satellite systems like GLONASS, Galileo from Europe, GLONASS from Russia, they do, and China, 𝐀𝐩𝐸𝐻𝐿 and NAVIC are regional satellite systems belonging to Japan and NAVIC. Most of the GPS are in mid-Earth orbit. But for example, like 𝐀𝐩𝐸𝐸, they use some different technique. It's like highly elliptical orbital satellites are there. GPS or GNSS signals are from code division multiple access technique is used there. Each satellite has its own unique code. But some of the GLONASS satellites use time division frequency division multiple access as well, which means the frequency bandwidth. So each technique has its own limitations. They have been studying this for years and done research, and okay, so CDMS suits better. That's how the receiver identifies the signal from which satellite is this coming to. Like I mentioned about the number of satellites, because early days, because it was like when you are looking at the receiver, it's like 2, 3, 4 satellites, and then damn, I won't get a position fix, or the time to first fix will take very long. But now you have number of satellites. I mean, I'm also surprised that we are getting sunlight because there are that much of satellites on the sky. So if you have seen the constellation of China, probably Sri Lanka, they have the Sri Lanka is very much covered by those satellites, and nothing to worry about. So this is what happens in the satellites. So the data code is in a digital format, and then it's exclusive OR onto a PRN code. These are also called goal codes. So, and then the goal code is mixed with a multiplied with the carrier frequency. And BPSK is binary phase shift keying. It's a modulation of signals. So if you are into signal processing and stuff, you can of course find many information, or you can decode the satellite signal and do stuff, try to maybe jam or maybe spoof the signal, introduce errors, or this is an area of application if you are more into signal analyzing and stuff. There are various reasons for these techniques, why this frequency, why this PRN code, and what happens, what are the advantages, what are the disadvantages. I'm not going to discuss theories or anything which will make me use equations. I will just focus on the applications. This is the data structure, like everything, this is the package which you are getting. So if you see, like if it's 0 and if it becomes 1, the phase of the carrier signal changes in between, just to indicate whether this is a 1 or a 2, and the process inside the receiver is also kind of an advanced, not kind of, it's very advanced technology which uses kind of many tricks to decode the signal and start identifying the starting point, because it's derived using autocorrelation between the signal. So the receiver itself starts generating a copy of the signal, and then let's say it has like 30 different codes, so it starts matching with the satellite signal to identify which code am I receiving, and using various iteration techniques you can get the position with the distance, and by the distance you derive the position. So this is an overview of the signal, this one, the data bits. So you need to find the starting point exactly, and it can be from one of either 5 subframes. You get the satellite clock and health data. There are first derivative, second derivative clock parameters due to the shifts, like because some satellites use cesium clocks, and then there is hydrogen mesa clocks. So based on those types, there is a small difference, and the receiver is using a very cheap OCXO or TCXO clock. So there are techniques that synchronize the very precise atomic clock with the very less accurate receiver clock. Ephemeris data is the data of the satellite orbital parameters, and almanac is the satellite parameters from other satellites in the constellation. So almanac is not that accurate. Ephemeris is kind of accurate, but it depends on the constellation, because in like some constellations, they upload the correction parameters every 24 hours. Some do it every 12 hours. So between these 12 hours, though the satellite may change its course slightly, let's say a few hundred meters, it will be broadcasting a different location, which the master control station have already fed the satellite. So, I mean, if you are familiar with post-processing and stuff, that's what happened there. You get the actual satellite location corrections, clock corrections and location correction parameters from a different source and embed it to your result. So you know at this exact point, this is where the satellite was, rather than using what's transmitted automatically. Okay, so let's get back to the application part. So the thing is, like, I was asking the said sub-broker, what should I talk? Because like there are directly related applications, 250 to 300 applications. Instead, everywhere where there is location is involved, there is GNSS or GPS or whatever the technique which gives you the location. In navigation, in transportation, surveying and mapping, science and engineers like civil engineering, geodesists, or people who are in geomodeling, agriculture, forestry, all location-based services, medical emergencies, military, and it's everywhere. So I thought of speaking of the rail transportation because in 2019, I don't know the update now, like there was no GPS monitoring signal thing or any technique used for the trains in Sri Lanka. But train control and signaling, the traffic information, you can definitely monitor the positions of, you can cooperate and you can organize properly how the traffic control should be, how it's, because I remember like one of my students started investigating it, and in Sri Lanka, they're using quite an old technique to monitor the positions of the train. So like I was reading, and there are many accidents and many dangers involved in these unmanned level crossings in Sri Lanka as well. So this is an application where you can give your interest in based on the location information you can get if you mount a receiver to the train, and if you have some sort of a indicator which you can receive the signal, you can of course determine where the train is. You can create a warning system. It will be just a simple app on your mobile, and this is an area where you could explore using a real-world application of the GNSS. Some of these things I have taken from what's done in India, because I learned all this GNSS in India, and some of the slides are from the information which I have learned there. So what the ISRO does is, the Indian Space Research Organization, they have a warning system. They have their own communication satellites, and some sort of a GPS antenna is mounted here, and then you give a sort of a boundary, like if based on the location information and the speed of the train, this point passes, a message goes to the communication satellite, and it will send a warning signal to the particular unmanned level crossing, and then all the people who are nearby will be warned. So now the technology is much advanced. So I mean, it shouldn't be a hood, it can be an actual automatic railway gate, because what happens is, I think there is a guy, what's actually there in Sri Lanka is there is a guy in the gate post, and he gets a call or some Morse code, and then based on that, he closes the gate. So sometimes even the train is not there. I mean, you have experienced that, like sometimes due to wrong information, like half an hour or 45 minutes, you'll have to wait in the queue before the guy opens the gate back again. So if the person knows where it is, like that's a key point, knowing where you are. I know it can compromise your personal information. Some people don't want to indicate, okay, where I am or something, but That's the power, the information of knowing where other entities exist. So this is an application which you can apply if you are interested. You can develop a sort of a small mechanism, mount a small GPS antenna on the train. So I'm not going to talk about the algorithms and all because the train is in a very high-speed moving platform. Of course, the receiver is stationary. So the algorithms are kind of different than the ones which are used in surveying applications. So this is just what's happening here. Like either you can get it to a mobile phone, or you can have an automatic gate and you can get the signal to that place, or you send it to a different server, something like that. But the thing is, in the system which is used in India, they have their own communication satellite system. But in Sri Lanka, I mean, I thought it's not possible to suggest to send a satellite, but I think last time the guys who are involved in this space have tried to send a balloon, and I think it was successful. So, I mean, you can prepare a proposal and you can suggest this to do, okay, let's dedicate or at least include the payload, which for whatever the satellite, maybe from another country as well, some payload from our country as well to do this communication stuff as which can act as a warning message. Next thing is, of course, road transportation. That's, I think I don't have to explain you much about this because it's like every day. I mean, if you open Google Maps and everything, cargo controlling, load monitoring, safety and security, e-tolling, especially if you are entering a very urbanized area, there can be tolls to control the traffic and preventing vehicle theft and all. This is all GPS and GNSS, which gives you the location information, which comes with an inbuilt. The thing is with this road transportation is, I will explain a project which I did as well, because if you want to monitor your car or anti-theft or anything, these sensors, there are sensors in vehicles, but those vehicles are quite expensive. I mean, not in three-wheelers or bikes or anything, but in very expensive cars, you can find like when there is an accident, there is an automatic call or a message is going to somewhere, and you can obviously get help on time. So this is like, if you are into this, if you think this is interested, you can create your own tracking system or own system which will track the vehicle, or if it makes a collision, or if it get into an accident or something, an automatic message can be sent from the vehicle to the a server or the nearest hospital or the police station, and so the main three units are the receiver, the tracking server, and the user interface. I mean, these are I'm just giving you the topics which you should explore. But when you are trying this in real world, it can be challenging. You will have to start studying from the beginning if you don't have any knowledge in electronics or mechanical engineering. You'll have to look into how the signal structure is. You will be getting an NVA message and how to decode the message. But it is doable. Something quite important, I think, in our countries. Because if you look into statistics, there are many accidents and many deaths due to those vehicle accidents. So this is just a guide or sort of thing. There is a tracking system on the vehicle. Then there is a server where the messages, where the communication will be done. Then there is the user interface. Either it's a GPS modem installed on your GPS device, or a display installed on your car, or either it's your mobile phone, something like that. The next thing is air navigation. Actually, this is the main reason for introducing the GPS in USA for civilians. It's for air traffic control, because earlier days it was like localizers and radar antennas, and the thing is the airplane routes were very long, because those infrastructures are very expensive and it should be fixed on ground. You can't fix an antenna in the middle of the sea. So one of the main advantages was using this GNSS technique on the aeroplanes to safely navigate, this ensuring the safety of the passengers. And also the introduction of SBAS systems, the augmented satellite systems, which will give you the corrections, increase the position accuracy, is also for air navigation. So this is what they do in ISRO, like the 𝐀𝐩𝐸𝐸 signals, which comes into L1 and L5 frequencies. There are actually 3 satellites, but one is spare. The GSAT 8 and 10 is operational, I think. This is augmented satellite system, which gives the correction parameters to your position. Because, for example, in the equator region, like Sri Lanka is in the equator region, so the ionospheric effects, the water fountain effects, the bubble, the bubble effects, there are so many, it's very turbulated rather than in mid-latitude or high-latitude regions. So the GPSs or GLONASS or those things are designed not for the equator region, but for high-latitude and mid-latitude regions. So what India did was they have their own grids which calculates the ionospheric corrections and interpolate to the location, and they transmit it to these GSAT satellites, and you get it. The signal structure is the same. So the receiver is capable of reading, and you get the exact correction on that for that moment regarding the ionospheric, because that gives you the highest error. That's the ionospheric correction, because the frequencies L1, L2, and L5, the effect is very much high. There is something called a group delay and a phase advance between those signals because of the ionosphere. Then, of course, we comes to the maritime applications. The thing is, you've seen like many times boats cross borders, but if it's Indian boats that crosses the Sri Lankan borders, like they have already installed this particular it's like a sealed package inside which can communicate with these satellites. It gives you the location, and if you cross the borders, it gives you a warning system, warning alarm. Okay, don't cross here, or it's a warning sound or something like that. So that comes in very handy, because if you are in the middle of the sea, and the thing is, if it's huge vessels or very expensive ones, fine, you have a GPS and all. But people who are doing fisheries and those small boats, they don't have those advanced displays which will show you, okay, where I am. And you can't even get a phone signal in the middle of the sea as well, because there is no infrastructure to get the mobile coverage. So this comes in very handy. I mean, if you think this can be applied to Sri Lanka, you can definitely see, look at the opportunities of doing or applying the GNSS technique into boats. And so the background will be different. So you can see your equipment, just receiving the signal is not enough. You must look at other aspects as well. How can I make this water seal? Sometimes maybe fishermen can deliberately try to change the thing and falls, or try to remove the instrument if they think like, okay, I need to cross the border and go because the fish yield is much better in that place. So you have to think in those aspects as well. And since there are no dedicated communication satellites, how to manage that part, like how strong the signals should be, like. But this is something which you can apply for Sri Lanka if you are into, at least in a conceptual level, you can suggest these things. This is what I explained before, the situation for fishermen. This is already in practice by India, but so you can do the same for our country as well. Next thing is precision agriculture. That's very effective. Next thing is, if you are into remote sensing, and if you think you're good in image processing and stuff, you can do precise agriculture. For example, let's say that you create an automated software or an algorithm which will download the satellite images and monitor, and you can maybe look into those images and identify the exact locations. Okay, in this area, this crop needs more nitrogen. and in this area, this crop needs more phosphorus or something like that, or this place needs water, because what is practiced now is you actually, even though the plant needs water or something else, you apply everything together to the whole area. But what you do here is you identify the areas which needs the required fertilizers or pesticides, and then you and like if you search Google, you can see that there it's like 40% efficient, and it gives more 40% of like the 40 to 50% the crop yield is increased because of this. So agriculture is, I mean, important for anyone. Like we survived on the food we cultivate. So this is another aspect which you can explore. Can we do this in Sri Lanka? Can you create an automated thing which will some sort of an algorithm do and identify, okay, in this particular area you need this, in this particular area the greenness is much reduced, so it needs either water or it needs to be dried, or preliminary studies, how the soil is looking like. So this is also, again, with GNSS, because the location is with respect to GNSS. Time synchronization is also another aspect which we don't talk much, because we talk about location. The other thing is timing, and because atomic clocks are the most precise instruments made by mankind. So it's like 100 nanoseconds, some 10 to the power minus 19 stability is there. So if you look at your mobile phone, if you have withdrawn money from an ATM, you can see the time, and that's synchronized to the GNSS time network. There is a separate timing network. The algorithms are different than calculating the location. In financial markets, stock exchanges, everything like that. If you have tried those forex market stuff and Bitcoin investing and stuff, you see that the time is very crucial there. Especially when you're dealing with countries and the aviation people, when you're dealing with other countries, that should be very precise. And this time is synchronized with GNSS timing. So another application, if you're interested, fine. I need to look into more time, how the time is calculated, how those algorithms are working. Maybe I can increase or use it for some other applications, like, for example, in power grids. I think if there are students who are doing electrical or mechanical engineering, they must know that these switches must be switched on at the exact time. Otherwise, there can be many problems. It's based on the wave, I think. So those precise switching ons are done using the time extracted from GNSS timing receivers. And we come to the location-based services that also, of course, you know, based on your location, where you are, how, and especially in commercial things also, like, for example, if you are in a shopping mall and if you are near Adidas, you'll be starting getting Adidas advertisements on your mobile phone, and you go to a Puma shop, maybe you start getting brands which related to Puma. So these are the things that are in practice, especially for the market, revenue market. People are like using those location information to show you, like, for example, in Google, if you search something for a product, let's say hard disks or something, then you'll be start seeing hard disks everywhere on your social media and everywhere. So it's the same. Your position information is also shared as well. So based on where you are, you will start getting advertisements and all the other stuff. So this, I think I don't have to explain much. This is in your mobile application. I mean, now they have given the Excel, you can search for where is the closest restaurant, where is the closest hospital or something. But the thing is, since we are talking about applications, there are aspects which are not involved in the location. For example, Google Maps will give you the quickest way to go, but the other aspect, let's take an example. Let's say there is a handicapped guy and he want to go to a restaurant in an area where it's very much flat and it shouldn't be much undulated for the guy. So then you have to take a DEM into account and also give a certain influence from based on the DEM as well, which route to choose. So I know these location-based services, there are many apps and all, but there are much less, focus has been, it's not much focus for aspects like that. So if you are into GIS and stuff, you can do a multi-criteria decision analysis and give some sort of weights to other aspects as well, the undulation. Maybe you can input the weather report as well. And based on that, you improve the decision making. That's the trend now, actually. Just not the quickest route or the fastest route to go. It's like, why? Because, for example, if you have read about agent-based modeling and space syntax and stuff, you see like, though the route is quite short, people tend to go in the longest route. Maybe it's because of the trees, maybe because I like the road. This is all understanding how a person thinks and modeling. So for those agent-based modeling and stuff, you obviously need GNSS. And surveying and mapping. So in our faculty, it's, very much, it's explained or taught in depth, like in a very advanced level. Students who are doing and surveying and geodesy, they have, I think, 3 or 4 subjects. So especially for establishing control points, measuring boundaries, cadastral construction and everything, you can use GNSS. The thing is, then you have to go with differential GPS, which means it actually should be DGNSS, not DGPS. Like there is a control point which you know the location, then there is the rover which you don't know. So just once you receive the location information from the satellite, once the receiver decodes it, you get the correction parameters from your base as well, like the coarse network. So that technique will give you a millimeter level of accuracy. So if you are into this, you can study more into the integer ambiguity resolution algorithms, and those sort of applications are there. You can define your own correction parameters rather than using what's coming in the instrument by default. Then we come to sort of research-based studies. The thing is, as I told you, the signals which are received from the navigation satellites are affected by the ionosphere. So based on this, how changed they are, like the influence the ionosphere is putting on these signals, you can do ionospheric studies. This is called, it is not new, but if you are into GNSS and you think I am interested in space weather and ionospheric, all those cosmic rays and stuff, you can explore this. There are sites which you can download this RO data from, I will put it in the chat. So what happens here is the receiver and the emitter, or the transmitting satellite, that's obviously spaceborne. The receiver is also in a low Earth orbit satellite. So it's spaceborne, but there are sites which will give you that data. So based on those data, you can calculate or do studies on the atmosphere, the vapor content, the pressure, and those sort of stuff can be calculated based on the bending angle. Actually, GNSS RO is a remote sensing technique, but since GNSS also gives the same influence, it's used in GNSS as well. This is the technique. Like this alpha is what you should calculate. So this is this L1 and L2 signals. And if you know the frequencies, and if you know how much alpha is, how much the value of the alpha is, you can definitely go into further calculations on studies of the ionosphere. So this angle, the bending angle, depends on the Doppler frequency, and this is the path. The excessive phase is what you calculate. From the excessive phase, you can get how much angle is, how much the deviation of the angle. This is because of the atmosphere. It can go through the atmosphere. It can be atmosphere plus troposphere as well. This incident happened for like 6 minutes. I think that's the time frame where you observe this difference because it's two very high-speed moving satellites. So I'm not going into calculations. That's very confusing. But this is an aspect which you can explore if you are trying for the NASA space apps, studying the because though there are many ionospheric studies done on the mid-latitude or high-latitude regions, the equatorial region is not that touched like Indians have done much. So these are the things because like the water fountain effect, the bubble effect, those sort of things are only common to us on the equator region. So based on that, there can be many applications on this radio occultation. So you calculate the excessive phase, then you get the excessive Doppler. From the excessive Doppler, you get the bending angle. So these are the parameters that we give. From the bending angle, you can get the refractivity. From the refractivity, you can get the pressure, temperature, and humidity. And from the ionospheric data, if you go into differential, you can calculate the total electronic content. Total electronic content leads to electron density. So I removed all the equations, but this is kind of the flow chart. These are the results. So from the bending angle, you can get numerical weather predictions, climate research. From the refractive index, there are many equations. I'm also not much familiar with those stuff because those are like more into physics and all. And temperature and pressure also, you can do atmospheric and climate research. The total electronic content is used in space weather models, because if you have studied, there are like NEQ or 𝐀𝐩𝐸𝐥𝐢𝐜𝐚, there are different ionospheric models used in those GNSS receivers. The problem is those models are good for the mid-latitude, but not for the equator region. That's why 𝐾𝐩𝐸𝐿 was introduced. And also the electron density as a function of actually the ionospheric research. So this is more into research, but also a very important application, because weather prediction is, now it's kind of better in Sri Lanka, as I heard, but earlier days, because it was saying if the weather department say it's gonna rain, it's not gonna rain. And if they say no, it's going to rain, it's not going to, the sun shines the whole day. So, but now I think it's better because some sort of satellite data information gives, like, if you can study the ionosphere, you can predict the weather in 5 hours in advance. So yes, then we come into GNSS reflectometry. The thing is, the multipath signal, it's very problematic to us as surveyors and as people who are observing, because you get an excessive path delay due to multipath. But the thing is, if you study the refracted signal, you can have an idea of the surface which it scatters. You can study the phase difference, you can study the properties of that particular surface. The thing here is you need a small config. You need to configure your antenna a little bit, because GNSS is right-hand circular polarized signals, but once it hits the surface, the polarization changes to the left-hand circular polarization. So, but this is another aspect. The good thing is, if you go, this is a remote sensing application which can also be done in GNSS. Like if you are using, let's say, visible satellite imagery due to cloud coverages and other obstructions, and maybe those sources are not free and you don't get 24/7 coverage, but a good thing is GPS, you get those signals 24/7 for free. So you can do long time series monitorings and all the to see the deformations or the changes and everything. An application of reflectometry is using it to calculate the sea surface roughness or wind patterns in the sea. That's very important for climate predictions and for sailors as well. this is an aspect which you can explore if you are targeting the NASA space apps using the GNSS reflectometry, or they call it GNSS-R. Here, they are using the time delay and the Doppler shift based on the, now in this image, it's airborne. However, you can have your own antenna. I mean, if you are doing it to the ground, or if you want to check the soil moisture or something, you can fix it on the ground. But if it's the sea, both the receiver and the transponder will be spaceborne or airborne. Based on, I'm not going to explain the equations. So it's basically the power of the signal based on the scattered power. You can calculate how fast it's moving or how rough the surface is. The point which emits the maximum signal is called the specular point, and this zone is called the glistering zone. It's a different theory, but simply it's an application of GNSS. So if you are into image processing, or if you love coding, if you love making equations into codes and creating algorithm, you can look into GNSS reflectometry as well. The next one is a disaster warning system. For example, if you, let's say that there is a landslide, or it's heavy rain, like for example, if you are entering Balangod area, there is heavy rain, there is a chance that there can be landslide. So you can design a system which sends to the user when you cross the borders, or when you enter that administrative border, to get a warning message to your mobile phone, like, okay, there is a chance, or like 50% or 60% chance of landslide, so either don't enter or take the risks, sort of thing. So it's, I think this application will be much useful in Sri Lanka, because when I was there, I had many experience, like the bus traffic was very huge. I mean, the road construction people should come, and then they should remove the thing. Until that, all the vehicles are stuck, and you are inside the bus cursing all the governments and everything. So this will be a good application, I think, if you can give sort of a disaster warning message to the user or to the relevant authority. It shouldn't have to be the user or the person or the passenger. It could be to a particular authority, because maybe though there is a landslide and the road is blocked, maybe the urban authority or the disaster management people don't know about that. So that you can create a sort of an automation in this regard as well. Then we come to the military use, which is not much focused in Sri Lanka. I don't know, I was working with some military group in Sri Lanka, which was a combination of Air Force and Army people, but I don't know whether they are functioning or not. They were exploring the drone aspects and LiDAR modeling and stuff at that time. So this is quite important for countries, and like if you look into many countries, much of their annual budget or the economy is more, or the funding is more gone on the military. And from military research, it comes back to the civilians. I mean, GNSS is also something like that. First, it was the DoD that used this, and then they gave it to the civilian people. So, for example, if you plan to aim a missile to China, and if somebody can spoof the signal and give you a wrong location, that will definitely go to, let's say, Myanmar or some other country, because all these things are automated. So this is kind of trending. Like if you are capable of decoding GPS signals, and if you are capable of introducing an error by yourself, if you can understand in that level, I mean, definitely you get enough. I'm not a supporter of military or anything, or any aspect that would hurt another human being, but it's a highly demanding area. There are two things actually, jamming and spoofing. In jamming, what happens is, if you look at an oscilloscope, you can see the signal. Likewise, what you do is you saturate that channel with your own signal. On the same frequency, you transmit a signal with a much higher power. So then the receiver cannot identify the GNSS signal. So that is just simply cutting off, transmitting a signal in a higher power. But in spoofing, what happens is you can fake the signal. You replicate your signal, and then you give some fake information. And then when you determine the location, you will not see where you are. For example, there are many security places where I live. And so when you go there and you search in Google, you can't see, it's either blank or you won't get those parts to navigate, especially near nuclear power plants and stuff. It's just people know, okay, there's a nuclear power plant here, but when you look at Google Maps, it's not there, or you won't never get a route, even though that's the quickest, which crosses those paths. So if you are interested, you can, of course, try to study the signal structure. That's a demanding application, try to spoof the signal. There are other various techniques how to detect the spoofing. For example, let's say that you are spoofing and your emitter is in your building. So when you transmit the emitter, the power of the signal is much higher than the signal which comes from the satellite. So by studying the power, the patterns, you can identify, okay, whether this is a spoof signal or whether this is a actual satellite signal. There are vector tracking algorithms and many other strategies. You can explore those strategies. Okay, what sort of strategies are there? Because there is another technology called pseudolights as well. So it's like everything which is on a satellite, but it's not space-bound, it's fixed on a building or on a high tower. So there are other location-based techniques like that as well. Of course, India uses for military applications their GNSS system. This is that which I explained to you as well. Another thing is what you can explore is the IRNSS and GPS coupling, because if you want very precise locations, the problem with IRNSS is with time, though the precision is very high, it gets degraded. So by terms, if you can use IRNSS is maybe a gimbal or stabilizer platform which has an 3 accelerometers and a gyroscope to move the rotation, rate of rotation and stuff. You can make a GNSS receiver coupled with the IRNSS. There are several coupling techniques like loosely coupled, tightly coupled. So you can give a correction to the IRNSS from the GPS. The thing with GNSS, though the precision is low, the accuracy is high. So let's say you give 2-3 minutes interval correction parameter to an IRNSS. And those algorithms, what sort of algorithms can you use, how to increase this? Maybe you can use a Kalman filter and all. So those applications are there as well if you are into, but that's like very heavy mathematics. Yes, so I will also show you a project just to get an idea how you should start designing or everything. This is on a conceptual level, but one student did this in practice for his final thesis project. The thing is, if you go into this is some project which I did in India, but you can definitely apply in Sri Lanka as well. The thing is, as I told you, in many expensive vehicles, you can find those units where you have an automatically alarm system. But for three-wheelers, for bikes, no, not for cheap vehicles. So what you can do is, this is just my motivation for the study. You can create a sort of a system which will give you a alert, or which can create a warning system. So this is the part which I wanted to show you. So what we did was, you can find shock sensors, airbag, activators, sensors, accelerometers. If you just walk in Ford, or it's very cheap, it's not that expensive at all, or you can order from eBay or Amazon. You can find many sensors, fire sensors and smoke sensors. Then there is a microcontroller processor which does the decision making. and of course a GNSS receiver, which all this information is received to this microcontroller. So GSM modem also, it's the simplest circuit board in a mobile phone. You can see, not these advanced smartphones, like the most basic ones you remember in like Nokia 1100, those sort of things. I mean, you can put a SIM card and they are capable of doing very basic functions like push messages or voice calls or sort of things. So what happens here is, if you meet with an accident, these sensors gets activated and it gives the message to the, then you have to create a truth table as well. Maybe this can be a false, maybe it can be a true. Do you want all the sensors to work and then activate this message, or do you think 3 of them is enough? So it's up to you to use which sensors. And then from the GSM modem, you can transmit this location. For example, maybe it can be an identifiable message, or maybe it's a code, but you can either send it to a emergency service, the nearest hospital. So then it comes, the GIS is coming into play, the hospital's police station, and you'll have to do a decision making based on where is the closest police station, where is the closest hospital. And then you will have to maybe look into OpenStreetMaps and use that data as well. So the thing with GNSS, it's not alone an application, it's mixed with either other disciplines as well, remote sensing or GIS or whatever it requires. And then either you can program the microcontroller to give a call to the emergency contact, or whether send it to a mobile app or mobile platform. But then you have to think of, like, in an accident, mobile phones can get destroyed. What happens then? If it sends to an unit in the GPS, but if the car is heavily damaged, then that unit can get destroyed. How to access that problem? So best thing is to send the message at the moment to all the police stations, hospitals, your loved ones on the mobile, or the emergency 119 or something. And then then you'll have to calculate how much time will it go based on the impact. And then you must see, because this unit can get destroyed inside the vehicle if you meet with a kind of a very large accident. So these are the aspects which you should see. I mean, when you are doing in practical, what comes, the real problems, what comes. This is the modem which you can use. I mean, you can find all of these on eBay or on Amazon. It's very cheap. But these sensors are there. You can program them. These are very cheap strap-down sensors. Shock sensors. So you can install these in your car or your vehicle. It's a three-wheeler or a bike or whatever you think. This is what we use, but you can use your own choice. This was on Android. So you can just program the codes to make what signal to be received from these ports. These are just the advantages of why we are using Arduino. Sensors and the tracker. So this is kind of a truth table. If this is active, the message is sent. If this is active, the message is sent. So you can give thresholds. Like, the problem is, if there is an accelerometer thing and if you suddenly brake but does not meet with any collision, maybe there is no accident, but there can be a false message sending to the authorities. So then you have to think of those aspects as well, how to prevent that. How should I give a threshold value? Okay, if this exceeds this value, or if the shock level exceeds this particular power, then they should get, this message should be sent. The budget. So it's quite cheap. So that's what I wanted to show you, and I made some links as well, so that I thought that if I share these links with you, for example, GNSS is used for geoid modeling. There is a technique which uses gravimetry data with GNSS data to improve the vertical accuracy from using geoid models. So you can download the data from here. If I send it to the chat, I think everybody will be receiving it, right? So yeah, I'll put it in the chat, these links where you can download the, this is for geoid models or gravimetric gravity models. Here you can get the radio occultation, which I explained, the airborne receiver and airborne emitter. For ionospheric studies, if you are into those applications, you can download data from here and in this one as well. So I've used this one. This is the official IGS sites to download precise orbital parameters and clock corrections. If you want to study those, if you want to look into RENX files, formats, how the file structures are, can we improve this, or is this efficient and stuff? Or if you want to study the satellite perturbations, how, for example, I can suggest you something like this. So there is a 12-hour delay from the master control station to the satellite. So by somehow, if you can decode the signal and get the raw pseudo range, so you get the actual pseudo, the actual information from the master control station from this side, side, and then you get what the receiver is getting from the transmitted signal. And from those difference based on the time, the XYZ and the time axis, you can develop an algorithm to predict rather than using this data down. Because if you know, I mean, if you are doing post-processing, probably now new softwares, they automatically download from these servers. But in some cases, those servers break down, and that's a big headache. You'll have to manually go and download the files and then input them to the your processing software. So you can develop maybe a neural network to predict, increase the prediction of these orbital parameters. This is not related to GNSS, but I thought of sharing with you. If you are into satellite images and Sentinel data can be downloaded here. These are, of course, you know, for Landsat and SRTM images. So I hope you got something from this, and you can maybe use these links to download data and study these data, study these applications. I will be sharing these PowerPoint with the 𝐀𝐩𝐸𝐬 people. If you have any questions, or if you think I'm wrong, no, this is incorrect, or if you want to argue, or if you have your inputs, feel free to share with me. I think there will be a question and answer session, so you can ask any question if you have any doubts.
Thank you very much, sir. If you have any doubts or feedbacks, the time starts the Q&A session. You can ask them and clarify via chat box. So unmute your microphone and ask them directly.
If you choose a receiver that has power as an yeah, I don't know whether you can, it's a direct message to me, right? So one question is, if we choose a receiver that has a power as an atomic clock, can we get more accurate position? It's not the power that we are interested in, it's the accuracy of the ticking, like 1.023 megahertz exact ticking of the atom which goes up and down. That will give you. The problem is that's very expensive. You will never be able to purchase a GNSS receiver if you put an atomic clock, and it's very big. So now they've made some mobile sizes. It's like 1 meter sort of thing, but these are very heavy equipment and very expensive. So it's not practical for users to get. But the thing is, there is a technique, sort of an iterative process, which synchronize the TCXO or the OCXO oscillator with the atomic clock frequency. So it achieves the same tapping, same sort of frequency as well. But if the signal, if there is a loss of lock or a slip in the cycle, then the synchronization breaks. But you don't need to have that in your receiver. Of course, if you have an atomic receiver, the calculations will be much simpler. Are there any atomic clock monitoring stations? It's not like atomic clock monitoring stations. It's once you fix the atomic clock into the satellite, you give and guarantee, okay, this is okay for 5 years. But that's basically because the fuel of the satellite, and it's, I mean, the satellite contains, it has a fuel tank because it should be navigated. It deviates from its paths, and then the master control station will send some sort of a signal, okay, take 100 meters to the right. It's not 100 meters, but just hypothetically. Then it needs to switch on some of its propellers and move it back to the track. So there is no like atomic clock monitoring station, but there are separate institutes which maintains the standard of these atomic clocks, which manufactures. So it doesn't, I mean, as I can remember, for 119 years or something, 1 second will be changed. So it's very accurate. Same frequency in S-bar signal and L1 signal. Yeah, L1 S-bar is actually in L5. In L1 also it's used, but in most commercial GNSS receivers, they use L5. I think only in NAVIC they are allowed to use, but if your receiver is L5 enabled, of course it has S-bus corrections. So it's much better. I mean, my suggestion is I have seen like many commercial people, like if you pay an amount, you can get a correction service like Trimble gives that, Leica gives that, but those are for their regions. It's S-bus is free, and so get it. The one of the problems is it's dedicated for GPS, because at the time that was the only thing on play. So you will have to separate it. I mean, either use a combination of corrections with all constellations plus S-bus with GPS corrections, or either use only GPS and S-bus. Please, okay, contact information. I can type my email here. Yeah, you can either email me or call me. That's fine. Or just contact anybody who's on said Sabra. They are in touch with me. Any more questions? In the second one, the person has put in brackets, I asked this because monitoring sessions are used to build global augmentation. The thing is, in augmentation, there is no global augmenting system. It's like localized, like IGNOS or GAGAN or sort of thing. The global people, there are paid services which you can get a global coverage via communication satellites, but it's a little bit different because in augmenting system, the signal is exactly the structure of the GPS signal, but in those augmented communication satellite signals, it's different. The structure is different, the signal structure. You can choose atomic clock for monitoring. But master control stations obviously have monitoring atomic clocks with them. Yes. Okay. The best thing for GNSS is it's everywhere. I mean, it's latest, it's new technology. It's a mix of various fields. So just Google it and you will get, but I'll send you the ICD. I mean, this is like the Bible for GNS. You can find everything. Oh, that site cannot be reached. I don't know why. Just search for ICD GNSS, interface control documents, and everything is there because the GNSS people, I mean, the receiver manufacturers needs the ICD. Looking at the ICD, they can manufacture receivers. So that's not confidential information, that's shared with the general public. There are receivers called software-based receivers. So it's another application. If you want, if you love the research, if you love these electronic parts and all, you can create a software receiver as well. There are PDF files, you can download them. But there are many YouTube videos, many people, Chinese, Indians, Europeans, USA people, it's not, I mean, you can find information everywhere. I've never seen where people share false information other than in comments or in blogs or something like those official websites. They give very reliable information and very reliable sources of learning. Try to look into the ICD. I mean, I know it's very hard to digest because it was really hard for me as well. You need a very thorough electronics engineering background. Like when I was doing the courses, I was the only guy who was into surveying and mapping. All the others were electronics people who are in electronics engineering and mechanical and electrical engineers. But in the application part, I don't think it is that complicated because simply you have a location. So you must look into what can I do with this location. So any more questions?
I guess all the doubts are clarified now. Is there any more doubts? And thank you, sir, for that amazing session. And I believe it was such an informative and valuable session for all of the participants, and got a lot of knowledge. Thank you very much again, sir. And also allocating your valuable time for us. And I pay my heartiest gratitude for the sake of 𝐶𝐸𝐻. And thank you all the participants. Stay tuned. The third session is on the way. We will meet at that, and goodbye and stay safe. Thank you very much.